Hello everybody. In this video we're gonna start the revision on the basic concepts that we need to understand and grasp well before we go ahead and start the derivation of the general molecular diffusion equation. And this is important because these concepts are the basis on which the calculations would be made, and it's important for everybody to be aware of these details. So I'm gonna pass by them quickly. I'm not gonna spend that much time on them. So the first is the difference between scalar and vector quantities. And I think this is a well-known thing, but I wanted to revisit it and kind of revise it quickly so that everybody is aware of what is the difference. And I think it's clear that the scalar quantity is just a quantity that is fully described by its magnitude. It doesn't have any direction, and examples are volume, mass, time, concentration, mole fraction, whatever. So if you define the volume, then this is all what you need to know so that you fully understand the volume. And it's like you have here, this is if you have two components here in A and B in the mixture. So if you say that the composition of A is 40%, or the mole fraction is 40%, then this is all what you need to know. However, in case of vector quantities, this is a quantity that is defined by two pieces of information: the magnitude and the direction. An example is the flux, the rate, the velocity, and this is like kind of informative image of the flux distribution in a pipe. And you see here that the flux has different directions depending on the place. So it might have the same magnitude, but it will have different directions, and this is why we have these arrows that show you how the flux is, or what is the direction of the flux at each point in the flow. That's why if you just define the flux by the magnitude, this is not going to be enough, because you have to tell what is the actual direction of the flow. And that's why for the flux we define it, or for the vectors in general, we define it using this form. We say that there is a component in x direction, and this is the unit vector in x direction, and it has a component in y direction, which is the unit vector in y direction, and this is the component in z direction. So you define it by defining three components, each in one separate direction. One way or one thing that we need to keep in mind is that we differentiate between a vector quantity and the scalar quantity by the putting the vector in bold. So you'd see that NA is written in bold to differentiate between the vector quantity, which is the flux, and the scalar, like the concentrations, like the mole fractions. One other thing which is important, and we will see a lot, is this symbol, the inverted delta symbol, which we call nabla or del, and this is in this case we call it a gradient, and this is when we do this gradient to a scalar quantity like concentration. And I'm putting all these equations in terms of concentration because we use concentration a lot, so this is going to be the most convenient thing here. So this is what we call a gradient of a scalar quantity. We can write it as grad C or nabla C. And this is, as we mentioned earlier, this is the derivative of the concentration or of this scalar quantity with the three space variables, with x, y, and z, r, theta, and z, r, theta, and phi. So this is the derivative of the c with respect to each one of them in case of Cartesian coordinates. And you'd see that the gradient of C is a vector quantity because we have a component in x direction, component in y direction, and a component in z direction. So it is a vector quantity. So it converts a scalar quantity to a vector quantity. We have three equations here because we can define a point in space in three different ways. You can define it in what we call the Cartesian coordinates or the rectilinear coordinates by knowing 3 points in space, x, y, and z. So if you know x, y, and z, then you know this point. However, in some cases, and this is by the way the easiest way of defining a point in mathematically speaking, but there are some cases where the Cartesian coordinates would not be very helpful, and these are the cases when we deal with mass transfer in pipes, in tubes, in cylindrical containers. So in this case you have another kind of coordinates that will be easier to use, which is the cylindrical coordinates. And in the cylindrical coordinates we define a point in space by the radius from the center line, the radius from center line, the height, which is z, and theta, which is the angle from this reference angle 0. So this is 0 angle equals 0, and this is angle equal theta, and this is r and z. So by defining these three you have a specified point in space using the 3 points. One last option or one last system is the spherical coordinates, and in these coordinates you define a point by the r, so this is the radius, theta, which is the angle with respect to this plane, and or this surface, and theta, which is, and phi, which is the angle with reference to this axis. So you have three information, r, theta, and phi, and then you can define this point in space. So for each coordinate system you have a different definition of the gradient of c or of any scalar quantity, and in this case you can see in cylindrical coordinates, this is how you write it: partial c partial r e r, and here 1 over r partial c partial theta e theta, and partial c partial z e z. In spherical coordinates it is kind of more complex, but it's still just an expression that you use, so it's not a big deal. If you use this del operator with a vector quantity like flux, for instance, then it's called divergence. It's not called, as we said earlier, it's not called the gradient, it's called the divergence. And in this case we multiply the del by a. We have the dot product del dot a. There are like some information or some details related to the dot product of vectors and these things. So if you're interested, you can check any textbook that is like more detailed, dealing with this operations in detail, because I'm just mentioning the important parts for us here. So this is all what we need to do. If it is a dot product of the del, or if we have a del of a vector, you can have it as a dot product, which is the divergence, which is what we can use. There are other cases where you have a cross product, but this is not of interest to us here, so I'm just mentioning this. So if this is the case, then it's going to turn the vector into a scalar. So this is it's not ex, ey, and ez as before, so it is just the derivative of a with respect to x in x direction, of course, and the derivative of a in y direction with respect to y, and derivative of a in z direction with respect to z. And this is the shape of divergence in case of cylindrical coordinates, and this is the shape in case of spherical coordinates. So this is the how we do the divergence and the gradient of vectors and scalar quantities. Sometimes you have a divergence of two quantities multiplied by each other. So if you have a product of two quantities and you want to get the divergence of these two, then it's exactly like the derivative of two multiplied parameters. Then you get the first multiplied by derivative of second plus the second multiplied by derivative of first, which is I think it's called by parts, if I remember it correctly. And this is what we'll do here. So if you expand this, it's going to be a multiplied by the gradient of b plus b multiplied by gradient of a. And there is something that's called the substantial or total derivative. We're not going to use it except for just one case, which is not something that we'll use in a lot in this chapter and in the coming chapters, but just to mention it in case you're interested. This is the total derivative, or sometimes called the substantial derivative, sometimes called material derivative, and it's written in uppercase dA divided by uppercase dt, which is the time derivative of the function plus the velocity in x direction multiplied by the gradient in x direction plus the velocity in y direction multiplied by gradient in y direction, and the same for z direction. This is all what we need to know about this, at least for now. The last thing that I want to revisit is the list of symbols. It's important to keep in mind the symbols and understand what each symbol means, because this is something that we will visit a lot. Sometimes people get confused because they are not sure what the symbol means, and that's why I put all the symbols here so that you have a chance to look at them instead of going back to the previous chapter videos and check them again. So here they are in case you are interested. I just want to draw your attention to the last four quantities here, or four rows here, which are all in bold because they are fluxes, and flux is a vector, so they are all vector quantities. And to differentiate between these two, which are different, this is not in bold, so it's not a flux, it is the number of moles of A, and this is the flux or mass flux of A relative to a stationary point. So it's important to understand the difference. So this is the last thing that I'm gonna discuss in this video. In the next video we will start, inshallah, with the derivation of the equation. So I'll see you then, inshallah. Goodbye.